So let's talk about ideal gas equations so that whatever that you see on your formula sheet, you can understand and interpret it according to the way the question will want you to interpret its answers. So remember that we spoke about Charles' law, we spoke about Boyle's law, we spoke about Guy-Lussac's law. So this formula is the combination of all of their principles into one formation. Now we talk about ideal gas laws or gas equations. So the properties must obey the rules of gases. Remember that if we have a liquid or if you have a solid, we're not talking about a gas. Those two are not gases. But here we're talking about ideal gas, meaning it has to be in a gas phase before it can behave as the rest of the other properties or particles that are in a gas phase. Now, remember that in Boyle's law we spoke about PV. We spoke about the product of these two. PV, this is Boyle's. Remember? Meaning that there is PV1, PV2, this is Boyle's law. And then now, we spoke about Charles' law, where we said Charles' law is when we talk about the volume and the what? And the temperature. So, this is Boyle's law, this is Charles' law. Then the remaining will be Guy-Lussac, in which Guy-Lussac we spoke about the temperature and the pressure. So, the same way, this is Boyle's law, this is Charles' law, and then this one became our our Guy-Lussac's law. So we combined all the thoughts and the understanding of how particles behave in a gas phase, and we make them one. And then now we spoke about ideal gas laws. But remember, this is pressure, this is volume, this is temperature. So now when they ask question to calculate ideal gas laws, looking at having the temperatures and the volumes of all those ones, you understand that if I have pressure number 1, volume number 1, and temperature number 1, then I'm going to either have temperature 2, volume 2, and I will need maybe pressure number 2, either way, depending on the questions, how is it given to you. Now, I need to differentiate all these ones all together so that you can understand them in this form. So, looking at this, we said that this one is who? This one is Boyle's. This one is Boyle's. It's B. Right? This is how you identify them. This one is B, is PV. Now we are moving to this one. This one will be our C, meaning that is our Charles' law. This one is our C, is our Charles' law. And then the remaining becomes our Guy-Lussac. The remaining becomes our Guy-Lussac. So looking at this one, we have this, in which is Guy-Lussac. This one is our G, Guy-Lussac. This one is our Guy-Lussac. So the ones with the white chalk is B, meaning that is Boyle's law. The one that is with the yellow chalk is C, in which is Charles. The one with the purple chalk is Guy-Lussac's principle. So from the principle that we used, we combined all the ideas, and then from there, then we're going to be focusing on how the behavior of this behaves, interpreted in ideal gas equations. So now we are moving to this one, where we understand that P stands for the pressure, right? So as the P stands for the pressure, N stands for the number of moles. The number of moles, in which is mole, the number of moles in stoichiochemistry, you did calculate number of moles, in which number of moles it was mass over molar, it was mass over molar mass. So in terms of this, you can still interpret, but the number of moles are represented by this. So supposingly you don't have number of moles, you can use this formula to get number of moles. The answer you get, you substitute here. And then now, let me take you through other aspects. So, and then T, remember that T is temperature. Temperature in which is measured in capital letter K, kelvins. And then V stands for the volume. The volume of the substance or the volume of the medium, the temperature in the medium. And then now we have the R. Now, I presented this for variables in which all these four variables will be in a position to assist you when you look at your formula sheet and how to interpret. So molar gas constant is R. Looking here, this R is always there on our formula sheet. Our formula sheet, R is always there, is constant there. And then we have what we call a standard temperature. And then in which standard pressure, not temperature, is standard pressure. This one is standard pressure. So the standard pressure is always given on your formula sheet. And then we have molar gas volume at STP. What is STP? STP stands for standard temperature and pressure, meaning that there is a standard of temperature and pressure. So looking at this, we are saying that the standard of temperature and pressure, in which the standard temperature and pressure is always there. You have the number or the magnitude of this pressure, you have the magnitude of the temperature, you also have the magnitude of volume, in which this volume is denoted by 22.4 decimeter cubed per mole, depending on but remember that it's only working when it comes to gases. These are working when it comes to gases. When it comes to solid, they don't, but they work when they are on gases. So, or when they are in volume liquids, they are not working, but they work when they are on gases, because this is the representation of behavior of particles in gas form. So this formula, we use it can be denoted by PV equal to nRT, depending on how you want it. But remember, P stands for the pressure, V stands for the volume, N stands for the number of moles, R stands for the molar mass constant, and then T stands for the temperature in kelvins. How do we find kelvins? We add, if it was given in degrees Celsius, we add 273. If it's given in 273, you want to convert it to Celsius, you minus 273, and then you'll get to where you want to get. So this is the ideal gas equations, and then how we interpret them. And then whenever you see equations looking at them, then we will be able to calculate them.